Let us go ahead and give it a try. Let us generate a test for D stuck at 1, let us see. So, we have D stuck at 1. So, in order to propagate, first thing is to activate the fault. So, I had to put a 0 here, that will activate the fault. Okay. So, a good circuit will have a 0, but the faulty circuit will have a 1. And in order to propagate it further, I had to put a 0 here, that will propagate the fault here. So, the good circuit will have a 0, the faulty circuit will have a 1. And in order to propagate this further, we need to have a 1 here. So, I have a choice, I can either take this one as 1 or this one as okay, I have not yet finished, right. I mean, this, let me see. In order to put a 0 here, I had to place either 0x or x0. Okay. And frankly, the moment I put a 0 here, this will become a 1. So, this is also x. Okay. So, I believe that will work. So, x0 0 or x0 x0 are both test vectors. So, x here means do not care. So, actually we will end up with possibly many vectors. So, 1 0 0 0 0 is a valid vector, right. 0 0 0 1 is sorry 0 1 0 0 is a valid vector, 1 0 0 0 is a valid vector, 1 1 0 0 is a valid vector. Then similarly 1 0 1 0 is a valid vector, 1 0 I think that is all, right. 1 0 0 0 is already a covered, right. 1 0 1 0 is valid vector. Hope I did not miss anything. Okay. So, all these are test vectors. Okay. So, let me show you one of them. So, let us try 1 0 1 0. So, a good circuit will produce a 0 here, a good circuit will produce a 1 here, and a good circuit will produce a 0 here and a 1 here, I am sorry 0 here. On the other hand, if the D is stuck at 1, okay, so D is stuck at 1, fault exists, that will cause this to become 1 and it will change this to 1. So, we have activated the fault and propagated to one of the outputs. So, we have activated and propagated the fault to a primary to an output. If there are multiple outputs, then we have a choice, we can propagate it to any one of the outputs. So, let me take another example maybe. So, I have multiple outputs here. So, let me label these as A, B, C, D, E. This is F1 and F2. Okay, this is G1 and G2. Okay, and this is H1 and H2. Okay, and let us say this is M and N. So, let us say we have a fault here, G1 stuck at 1, and we want to generate a test vector for G1 stuck at 1. So, we have to step 1 is to activate the fault. So, we have to somehow put a 0 here, so that that fault gets activated. Okay. So, we have differentiated between a good and a bad circuit. A good circuit will have a 0, but the faulty circuit will have a 1. Now, there are two things that we need to do. I had to justify the ability to put a 0 here. That means I have to see, I can't directly put a 0 on G1, right. You have to appreciate that we have to control G1 to 0 value indirectly by controlling C and D. Okay. So, I could possibly put CD equal to either 0x or x0 or no, I am so sorry, both of them should be 0. So, CD must be both 0. So, only when I put both 0, I will be able to put a 0 here. Okay. So, I have been able to activate the fault. Okay. I can control G1 fairly easily by setting C and D to 0. The next thing is to propagate the fault to either M or to N. So, I have a choice. So, try propagating the fault to M. Okay. So, if I do that, I have to make this 1. Okay. Then what will happen if I want to make 1 F2 equal to 1, then I have no choice but to make A and B 1. That will cause F2 to become 1, but unfortunately that will also cause this to become 1. Okay. So, though I propagated the fault to this guy, this 1 will kill the fault. So, I cannot propagate the fault to M. Once again, I managed to activate the fault by placing a 0 on this line. Okay. The good circuit will get a 0, the faulty circuit will have a 1. So, that activated the fault, but in order to propagate it further, I need to put a 1 here, okay, because it is an AND gate. If I put a 0 here, then the AND gate will get a 0 no matter whether the fault is present or not. So, I do not want that. So, I need to put a 1 here, but in order to put a 1 here, unfortunately, I have to put a 1 here, that causes a 1 here. This is a fault free circuit, it will go directly and that will become a 1. So, M will become 1. So, that is not going to help me. So, now we will try to see whether we can propagate the fault to N. To propagate the fault to N, we have to put a 1 here again. Why? Because if I put a 0 here, N will become 1 no matter what. whether the fault exists or not. So, I will try to put a 1 here, and that is doable by, see, we have already got a 0 here. So, we can put a 1 here. So, this will work. Okay. So, these are since I cannot propagate the fault to m. So, I need to not set these guys. So, I can leave it as XX. So, XX001 is a test vector for this G stuck at 1. Okay. XX001 is a test vector for G stuck at 1. Apply any values to XX, it could be 0, 0, 0, 1, 1, 0, 1, it does not matter. You have to make sure that C is 0, D is 0 and E is 1. Then take a measurement at N. Okay. If the circuit is good, then what will it produce? Let us simulate. I will get a 0 here and a 1 here and a 0 here. So, the good circuit will produce a 1, but a faulty circuit will produce no, wait a minute, I think this 1 is still required. So, we still need to propagate the fault here. So, my apologies, we had to have 1 1 here. We could not propagate the fault to M, but in order to activate this fault and propagate it to this point, see, I need to bring it to this point no matter whether I want to go to N or to M. So, I tried to go towards M, but I could not. So, in order to come here, I still need a 1. So, 1100 is a, so 11001 is a test vector for G stuck at 1. Okay. So, let us verify this. So, I apply 11001, simulate the circuit, 1 1 here will produce a 1, that 1 will come here, that 1 will go here, this will cause a 1, this will cause a 0 here and this will cause a 1 here, it will cause a 0 here and it will cause a 1 here. So, a good circuit will produce a 1. On the other hand, if I ended up with a fault here, a G stuck at 1 fault here, G1 stuck at 1 fault here, then that 1 will result in a 1 here and that 0 1 will come here and it will cause a good circuit will produce a 1, but the faulty circuit will produce 0. Okay. So, that is why we say 11001. So, the test says apply 11001 and measure the voltage or whatever, measure the voltage at N. If it is, let us say, if it corresponds to a logic 1, there is that G1 stuck at 1 does not exist. If it is 0, then output is, if it is 0, then fault G1 1 may exist. We can't say it exists, because as you know, there may be some other fault which causes the same problem. On the other hand, if we get a 1 at the output, then we can be convinced that G1 1 does not exist. Okay. So, I hope this fault activation and fault propagation are both clear. So, if I have a combinational logic and there is a fault, so these are my primary inputs and these may be primary outputs. So, when I say activate the fault, suppose this fault is a stuck at 0 fault, then I have to place a 1 here. Okay. So, placing a 1 at the fault site, okay, this is the fault site, some wire will activate a stuck at 0 fault. So, if you want to activate a stuck at 0 fault, place 1. If you want to activate a stuck at 1 fault, you have to place a 0. Okay. So, placing a 0 at the fault site will activate a stuck at 1 fault. And in order to do that, we can't directly do it, we have to indirectly control some of the primary inputs. So, pre-Is must be controlled to activate the fault. All right. The next thing is to propagate the fault to one of the primary outputs. It may be this fault, there may be other. Once again, we must control the PIs such that the fault propagates to one of the primary outputs. If it goes to more than one primary output, we have no problem. It should go to at least one of the primary outputs. Okay. So, that shows the problem which we call as controllability and observability. So, what is controllability? See, in order to activate the fault, I am asking you to control this value to 1. How easy is it to do that? Okay. It may be somewhat difficult to get this point to 1. Okay. As I told you earlier, that is the satisfiability problem. Can I send this wire to a known value like 0 or 1 by only controlling the primary inputs? So, that is a tough problem. It is solved by backtracking, right, and in the worst case we may end up trying all kinds of inputs at the primary inputs. In the worst case, all the 2 to the power n, if there are n primary inputs, I may end up applying all the 2 to the power n inputs. Then, having activated, I need to propagate the fault to one of the primary outputs, because I can't directly observe this line. I cannot directly observe this line. So, that is the problem of observability. So, in a very large circuit with maybe millions of gates, so if I have this wire and I have many inputs and many outputs, even to activate the fault, it may be a tough thing to do, and then propagating the fault by further controlling the inputs. Okay, so that is why it is this is not as, it is a challenging problem. So, this is called as test pattern generation. So, whatever we did earlier, we were generating test patterns. So, it is called TPG. Some people simply say test generation or TG. And if it is done with a program, see, we have not used a program here, we have tried to do it manually, right. For small circuits, yes, we can do it manually, but if it is a big circuit, it is virtually impossible to try and do manual test generation. So, when we do automatic test pattern generation, okay, that is called ATPG, automatic test pattern generation, or ATG. Automatic test generation. So, in the semiconductor industry, there are many tools or programs which are available, which can be used to generate test patterns for faults. Okay. So, there are many companies which sell such tools. For example, there is Synopsys, then there is Cadence, there is Siemens. Okay. These are three well known companies. They sell tools for various uh, design and test functions. Okay. So, each of them sells a tool for test generation. Okay. All right. That's so, if I give you a big circuit, right, the first thing to do is fault generation. What that means is generate a list of faults. Right. It could be all single stucket faults. So, we say SSF, single stucket faults. They can, tools can also handle bridge faults. Okay. But right now, let us talk about single stucket faults. Then the next step is to do fault compaction. So, we have to eliminate equivalent faults and dominant faults, and reduce the size of the fault list. So, let us say this fault list is F. F contains a number of faults like A0, A1 and so on. Now, we have to find a test vector for each of these guys.